In this video, we're going to talk about inflection points. What's an inflection point? Well, an inflection point is a point where the concavity of a function changes. It changes from concave up to concave down, or concave down to concave up. So you might have something like this, where it's concave up and then concave down. The concavity probably changes about right there. Or you could have something like this, where the graph is concave down and then concave up. If you think of this as a road, this is maybe the map of a route that you're taking, and you're traveling along in a car, maybe a little bit too fast. If you're traveling in this direction, as you're going around, let me change this. If you're going around the curve like this, while you're going through this part of the curve, your tendency would be to lean to the right, but as you reach the inflection point, that tendency goes away, and actually you start leaning to the left. So that's one way another way to think of the inflection points. All right. So how do we find intervals of concavity, intervals of upwards and downwards concavity, and inflection points? Well, the procedure looks a lot like the first derivative test for extrema, except that we're looking at the second derivative. So everything we did for the first derivative test for extrema, do that, only use the second derivative instead of the first derivative, and you've got the procedure for finding intervals where a function is concave up or concave down, and inflection points. So you find all the numbers where the second derivative of f is 0 or undefined. Now, instead of calling those critical numbers, some people call those hypercritical numbers. Then you find all the intervals that are defined by those numbers, and select the test number from each interval and find the sign. And well, we'll do an example. Find all intervals of upward or downward concavity and inflection points for the function f of x equals x cubed minus 3x squared. Now, I didn't mention it in the steps above, but you ought to look for discontinuities as well. But there aren't, since this is a polynomial, there are no discontinuities. So let's take the first derivative, and that's 3x squared minus 6x. Now let's take the second derivative, and that's going to be 6x minus 6. We look for all the hypercritical numbers. Those are places where the second derivative is either 0 or undefined. Well, the second derivative is never undefined. So let's set 6x minus 6 equal to 0. I think that gives us x equals 1. That's our only hypercritical number. So what we need to do then is look at the interval from negative infinity to 1 and the interval from 1 to positive infinity. We need our test number. How about 0 and 2? And substitute those into the second derivative. If you substitute in 0, you're going to get a negative value. If you substitute in a 2, you're going to get a positive value. So that means the original function is concave down and then concave up. And that's a positive one. And is there an inflection point? Well, if there is an inflection point, it has to occur at one of the hypercritical numbers. Our hypercritical number was 1, and on the left side of 1, the function was concave down, and on the other side it was concave up. Concavity did change direction, so x equals 1, and y equals, I believe it's negative 2, is an inflection point. And again, to find the y coordinate, all you do is substitute in the 1 into the original function f of x.